For your birthday, your parents got you 2 pet rabbits, just 2. 1 month later, you had 6 rabbits. And then after 2 months, you had 18 rabbits. And after 3 months, you had 54 rabbits. So you had a lot of rabbits, probably like taking up your whole house. This story can be described with the equation y equals 2 times 3 raised to the x, where x is the number of months and y is the number of rabbits. This is an exponential equation because the exponent is a variable. Notice that? Your exponent is x. Since the graph is increasing from left to right, we call this an exponential growth model. Starting at month 0, if I substitute 0 in here, 3 to the 0 power is 1. That's a strange thing that we forget sometimes. Anything to the 0 power is 1. So we get 2 rabbits. And so I'm going to put in my table of values 0 and 2. All right, and then let's see, month 2, and you know what I skipped over was month 1, so let's also do month 1 because we're going to need to fill these in. Month 1, y is equal to 2 times 3 to the first. Remember, using PEMDAS, order of operations, you have to do exponents first. So what's 3 to the first? Well, 3 to the 0 is 1, and 3 to the first means just 1 3. So it's just going to be 3. So I've got 2 times 3, which is how many rabbits? 6. Good. Remember, that was in the story. 1 month later, you had 6 rabbits. And then 2 months later, we have 18 rabbits. And we also know after 3 months, you have 54 rabbits. So the question is, how many rabbits do you have after 4 months and after 5 months? So we're going to substitute those numbers into the equation. And remember, our equation is right here. So I'm going to take that equation down here and substitute the 4 in there. 2 times 3 to the 4th. 3 to the 4th is not 12, right? It's not 3 times 4. It's 3 times 3 times 3 times 3. How many times did I say 3? I said it 4 times. Good. Because it's 3 to the 4th. So technically this is 2 times 3 times 3 times 3 times 3. It's a lot of 3's, right? You can split this up. What's the first 3 times 3 going to be? 9, right? And the second 3 times 3 is still 9. And then I got 9 times 9, which is? I think somebody knows. 9 times 9? 81. Thank you. So I have 2 times 81, which seems hard, but it's not really because it's 2 times 80 and 2 times 1. Anybody have it? 2 times 81. 162. All right, so when I have 4 months, I have 162 rabbits. I do not even want 162 rabbits. All right, and now I'm going to do 5 months. Still using the same equation, which is this one right here. So I put the 5 for the x in the exponent up here. 2 times 3 to the 5th. Now you can do it by hand, but you can also do it on Desmos. Let me pull up a Desmos real quick and we'll look at that too. Or you could even use the calculator on your phone. All right, so we have 2 times 3, and the 3 is raised to the 5th, right? And I get 486. Does that look right? I think it is. Okay. 486. So after 5 months, 486 rabbits. So we're going to make a table of values. We got that done, actually. We're going to do a graph, and then I'll show you what they mean by an asymptote. Has anybody ever graphed an asymptote before? Raise your hand if you remember doing that. Oh, it's fun. It's your very first asymptote. All right, so let's graph. 0, 2, we have to estimate because we got 20 on here. So 0, 2 is going to be really, really small. And then I've got 1, 6, also really, really small. Just like remember when we were graphing Avi and Benita and it looked like it was flat. It looks flat for a moment. And then I have 2, 18, so that's getting closer to the 20 line. 3, 54, that's going to be below the 60. 4, 162. Just above the 160. And then 486. Well, this last line here is 480, so I'll be above that. All right, so you can kind of see that exponential growth. Really nice in that picture. I just graphed these points right here. And you're going to sketch the curve. Try to make it curved. It's not like a series of lines. It really is a curve. This last part's the hardest part. An exponential function theoretically goes forever in both directions. However, we know we can't have negative rabbits, so I'm not going to keep going in the negative direction. But I could keep having more rabbits for sure. All right, so an asymptote is kind of an invisible line that your graph cannot cross. And for an exponential function, the parent functions have one at y = 0. And we're going to see on the back that these actually, they can move up and they can move down. But this is your asymptote. I draw it dashed to show it's really just like a wall that you can't cross. It's not a part of the function. The purple is the function and the green is the asymptote. And I'm actually going to just write the word asymptote on it. So because it's our very first asymptote, to remember what that is. Okay, so I did the graph and I did the asymptote. Oh, I didn't label the axes. See, this is why it's good to check things off. All right, so you guys remember what the x represents if you go back to the beginning? Anybody remember what the x represents? The x isn't the rabbits. What was the x? It is the months. Good. So I'm going to put months on the x-axis. And then I'll put rabbits on the y-axis. Okay, and let me just give people a minute to catch up there, and then we'll look at the back. There's not too much to do on the back. I'm just going to cross off, label the axes because I did that, and I'm going to turn the page. All right, so we transform an exponential equation the same way we transform those parabolas when we were doing quadratic equations in the last unit. You can still use h and k to move them left, right, and up, down. And you can still use a to stretch them. Stretches in exponential functions, they're really tricky, and so we're not going to do those today, but we are going to do the shifts. So here's the parent function. Notice that the asymptote is at y = 0. All right, and then notice that we have some key points here. 3 to the 0 is 1, and 3 to the 1 is 3. These are some key points to notice when we're trying to figure out what kind of transformations we have. So the first thing I look for when I'm trying to describe transformations of an exponential function is I look to see if the asymptote moved, because it's so much easier to tell than the points. So looking at the first problem, did the asymptote move from y = 0? Is it still at y equals 0? No, it's not. It's at y equals what number? It's right there. Yeah, it's negative, but you're right. So y equals -2 is the asymptote. Okay, so since my asymptote moved down, that indicates that my entire function moved down. How many? All right, so we're going to say shifted down 2 from the parent function. Good morning. Thank you. All right. So I'm going to give you a minute to look at these graphs and see if you think that they shifted down or up or left or right. And actually, I was wrong. We do have some A values in there. So you might see a stretch or a reflection in there as well. Okay? So take a minute and do your best to describe these graphs. And you can ask questions. You can talk to each other. All right, I see that a lot of you guys noticed that the asymptote did not move on any of these functions, so none of them shifted up and down, right? I did the easy one already. Did any of the graphs shift left or right in 2 or 3 or 4? Did any of them shift left or right? From the parent function here.
Number 2.
Which one?
Number 2.
Number 2, let's take a look at number 2. So number 2 has the same asymptote, but it does look like this point that was at 0, 1 has shifted to 2, 0. And then this point that was at 1, 3, it shifted to 3, 3. You see that? So the points, they shifted over to the right. I'm telling you, it's so much harder to see these in an exponential function than it is in a quadratic equation. So these did shift. So we're going to say that they shifted which direction? Right, good. All right. I think number 3 is the hardest one to see. Anybody have an idea what happened with number 3? So, like, it kind of seems like maybe it shifted left because this point is here, right? But that would be shifting a half of a box. And then the one that was at the 3, 1, it shifted more like 2/3. It's really hard to see. If it didn't shift, what else could it be? It could be stretched. And Kenny's agreeing? Yeah, it is actually stretched by 2. And there are two ways to see this. One is that when you see the number in front, that A value right there, that indicates a stretch of 2. And then when you see the values doubling, so see this 1 became a 2, right? And then the point that was at 3, it became a 6. See how they're doubling? So the one that was at 1, it doubled to 2. And then the one that was at 3, it doubled to 6. Okay, so this tells us that it is a stretch of 2 from the parent function. All right, and I appreciate everybody who has been participating here because these are tricky for sure. Who has a question before we do the last one? Okay, make sure you're writing this down. I'll be by to check off your work in a bit. All right, raise your hand if you would like to suggest something that might have happened with the last one. I'm looking for some hands because I have an idea that a couple people might have this one. I only see one hand. One student's brave. All right, Eamon, tell us your idea.
I think it got reflected.
All right, Eamon thinks reflected. If you agree with that answer, raise your hand. All right, a lot of people are being brave now. Very good. Yes, it did reflect. It was here, and it reflected over the x-axis. We've been calling that a vertical reflection. And that negative right there is what did it. From the parent function, of course. Okay?